In this third exercise of the fourth worksheet, we are going to solve this problem. Here we have a combustion reaction of glucose that is carried out in a calorimeter, and we are given the mass of the glucose and the heat capacity of the calorimeter, which is equal to 2152.3 joule Kelvin minus 1. The first question is to determine if the combustion reaction of glucose is complete. So to solve this exercise, we have first to write the combustion reaction. We have glucose of this formula it is a combustion reaction, so it will react with oxygen gas, which gives CO2 and water in liquid state. It is a combustion reaction, and now we have to balance this equation. Here we have 6 carbon, and also we have 12 hydrogen, so we multiply by 6, and here we have 12 oxygen plus 6, which means we have 18 oxygen. Now we have to add here 12 oxygen to the 6 to have at the end 18 oxygens. Now the equation is balanced. The first question is if the combustion reaction is complete. Here we have 6 mole of oxygen that react with 1 mole of glucose. However, in this case, we have used this mass, which is 4.324. So we have first to calculate the number of moles of glucose and to see how many moles of oxygen are needed to make this combustion reaction complete. So we have here the mass of glucose over the molar mass of glucose. Here we have said that the mass of the glucose is equal to 4.324 grams, and the molar mass of glucose is calculated from the molar mass of each atom, because we have 6 carbon plus 12 hydrogen plus 6 oxygen. All these are molar mass, which gives at the end a molar mass of 180 gram per mole. So here we divide by 180 gram per mole, and we get a number of mole of glucose about 0.024 moles. Now we have to determine the number of moles of oxygen. Here oxygen, we assume that it is an ideal gas, so we'll use the ideal gas equation. And the number of mole of oxygen is equal to the pressure in the bomb times the volume of the bomb over R times T. Here the volume of the bomb is 4 liters, and the pressure inside the bomb is 1 bar, which is about 0.98 atmosphere at 25 degrees Celsius. So here we have the pressure, we have set 1 bar, it's about 0.98 atm. So we can say it's about 1 atm also. And the volume here, it is 4 liters. So we multiply, we have 1 atm times 4 liters. We use the R, which is the value of 0.082. It is in atm, liter, Kelvin, mole, times at 25 degrees Celsius. In Kelvin is 298 K. So now, if we calculate now the number of mole of oxygen in this condition, we get a value of about 0.164 moles of oxygen. So now, in order to know if the equation is complete, if we divide the number of moles of oxygen on the number of moles of glucose, it must be at least equal or greater than 6. Because here we have 6 mole of oxygen are reacting with 1 mole of glucose. But here, in this case, we have 0.024 mole of glucose. And by dividing the number of moles of oxygen gas over the number of moles of glucose, we get a value of about 7, which is greater than 6. So we can say that the combustion equation is complete. Now, the second question, we will calculate the molar heat of combustion of glucose at constant volume. Here, the molar heat of combustion, it means that the heat that is released from the combustion of this mass of glucose. And because the calorimeter is an isolated system, so the heat that will be released from the combustion of the glucose will be absorbed from the calorimeter and the water bath. So it will be the heat that it released from this combustion reaction will be absorbed from the calorimeter and the water bath. So to calculate the combustion reaction, we have to determine the heat that is absorbed. It's the same thing, but they have opposite signs. And here we have the heat that is related to the calorimeter is equal to the heat capacity of the calorimeter times delta T. Plus, here for the water we have the mass of water times the specific heat of water times delta T. Now we can write as follows. C, the calorimeter plus mass of the water times the heat capacity of water times delta T. Now, we know that the heat capacity of the calorimeter is given, and here is its value, 2152.3. And also the mass of water, here we know that we have 5 liters of water at 25 degrees Celsius. And also the heat capacity of water, which is equal to 4178 joule Kelvin gram minus 1. And the variation in temperature is given as 2.92 degrees Celsius. So all these values are given. Now we can plug each value in this equation. So we start by the calorimeter. Here we have 5 kilograms of water because the density of water is 1 kilogram. The density of water is equal to 1 kilogram per liter times the heat capacity of water, which is about 4178, and the variation in temperature is equal to 2.92. Now we just do the math and we get the heat that is released from the combustion reaction. Negative 67,000 283 joules, or in kilojoules about negative 67.3 kilojoules. Now in this question it is asked to calculate the molar heat. So here we have this heat that is given for this reaction, for the mass of the glucose. In order to get the molar heat, we have to divide this given of energy from the combustion by the number of moles of glucose. And here it is equal to negative 67.3 kilojoules by 0.024 moles. So at the end we get a value of negative 2808 kilojoule per mole, which is also equal to the energy that is given of delta U. In the third question, we will calculate the standard enthalpy of combustion of glucose. We have the relationship between the internal energy and the enthalpy of any reaction, which is given as delta H is equal to delta U plus delta PV. And because the volume of solid or liquid don't change in a reaction, so here we'll take into account only the gas substances. Here we have oxygen and carbon dioxide. We have the only two substances. So here we have 6 mole of oxygen and 6 mole of CO2. Here we have a liquid and solid. So here we'll replace by their value plus delta N R T. R and T are constant. These values are constant. And delta N is equal to the 6 moles of oxygen minus the 6 mole of, or 6 mole of CO2 minus the 6 mole of oxygen, which gives 0 value. Therefore, all this is 0. The standard enthalpy of combustion, here also it is equal to this value in kilojoule per mole, which is also the standard enthalpy of combustion. In the last question, we are going to calculate the standard enthalpy of formation of glucose. Here we have to use the Hess law. We know that the standard enthalpy of reaction, or the standard enthalpy of combustion of this reaction of glucose, is equal to the sum of the standard enthalpy of formation of product minus the standard enthalpy of reactant. And by replacing in this equation, we have here the stoichiometric coefficient of carbon dioxide is 6 times the standard enthalpy of formation of CO2 in gaseous state, plus 6 times the standard enthalpy of formation of H2O in liquid state, minus the standard enthalpy of formation of glucose in solid state, plus the standard enthalpy of formation of oxygen gas. But for element, it is equal to 0. And we have to bring this enthalpy out of this equation. So now the standard enthalpy of formation is given as of glucose Now we can plug each value in this equation because they are all given. The standard enthalpy of formation of CO2, of H2O, and of the combustion reaction that was calculated in the second question. And by doing math, we get a value of negative 1264 kilojoules per mole. So here is the standard enthalpy of formation of glucose using the calorimetry experiment.